Class, I wanted to go over this difference amplifier example before class tomorrow, so you had some chance to review it, before class on Wednesday. So basically this is how we're going to do this. Now, difference amplifiers are always going to have two voltage supplies because you're amplifying the difference between these two voltages. Given it VB, you want to know what the range of VA is going to be, and then also figure out what's going to happen if we decrease this resistor over here. All right, so our first goal for this problem is to find our input voltage V. In this case, I'm going to call it VP, right? Remember, that's going to be measured to from our common node up to our positive non-inverting input. To find VP, this is actually going to be a simple voltage divider, right? Because we want to know this voltage drop across this 20 ohm resistor, we can just say, hey, the total voltage drop, remember that these are connected, so this is our total loop here. We can say our total voltage drop is going to be VB, so we can say voltage divider. Whenever we have a voltage divider, it's going to look like our total voltage. We're going to have an equivalent resistance, and we're going to have our resistor in question, which in this case, we'll call it R1, but that's our 20 kilo ohm resistor. So we got 20 kilo ohms here on top. Our total resistance is the sum of those two together, so that's 24 kilo ohms. And our total voltage is VB. So we can say VB, or VP, is the same as 5 VB divided by 6. Now, one of the things that's helpful here is using the ideal conditions. We know that for an ideal op-amp, that VP is equal to VN. And we also know that IP is equal to IN, which is equal to 0, right? And then we also know our last one is that we know that VO is going to be somewhere between our upper voltage and our lower voltage, supply voltage. I like to call it supply voltage, but it's really voltage relative to my common rail right there. All right, so now we know how VP. Then we get into the part where we start looking at I'm going to write this over here. Step 2 is finding our current, right? Finding our current, and we're going to take our current at using our node voltage method / KCL, and we're going to look at node N, right? Node N being this node right here. This is connected to our non-inverting input right there. We know that the current into this part, through this part, is 0, so we're going to ignore that. The only current we're going to have then is this feedback current that's coming because our output voltage is greater than our input voltage. So what does that look like? Well, we can think about it as I of our 10 kilo ohm resistor and I of our 50 kilo ohm resistor. Because these two things are the only currents coming in and out, they're going to be equal and opposite. So we can think about it like this. We can say, okay, what's the current coming out? Well, I10 is going to be VN minus VA. That's the voltage drop across this resistor. And the current then is just going to look like that voltage drop divided by 10 kilo ohms. And we're going to also do the same thing over here with the 50 kilo ohm resistor. That's going to look like V naught minus VN. All right, so now we got VN minus VA, V naught minus VN. I'm going to clean this up just a little bit here, so I'm a little bit messy. All right, then I can simplify. I'm just going to go ahead and multiply everything by 50 kilo ohms and make my life a little easier. Right, when I do that, this is going to cancel out. This is going to become 5. So I've got 5 VN minus 5 VA is equal to V naught minus Vn. Or I can say, okay, my V out just starts to look like Vn plus 5 times Vn minus Va. All right. So I've got that part. Now we know what this is all related to. We know the voltage, how they're related to Vn and Va. What I want to do is write it in terms of Vb though, right? I want to really get it in terms of Vb and Va. Those are the two input voltages that we're comparing, right? Va and Vb. So what I'm going to do is I'm going to use my ideal condition here that tells me, I'll use my ideal conditions right now. My ideal conditions tell me that Vp equals Vn. So Vp equals Vn, which means I can replace that Vn over here with 5 Vb over 6, right? I can replace that Vp Vn over here with 5 Vb over 6. So kind of plugging that in here, I'm going to plug that into this equation right here. Plugging that in, I get V naught equals, and I'm going to make this simple on myself. I'm just going to call this 6Vn. I'm going to call this 6Vn minus 5Va. So if I make this 5 times 6Vn, can actually just replace this and make my life a little easier. And look at that. I'm not really into conspiracy theories, but it looks like they made the math easier on us for some reason, right? So if I do that, I can simplify this, and this just becomes 5Vn. Vn, this should be Va here. And I can say, hey, this just looks like 5/5 Vb minus 5 Va, or V naught is 5 times Vb minus Va. And what I've gotten here is I now know my gain for this particular amplifier circuit, right? Remember that often our gain for these sorts of circuits is it's based on our resistors and not necessarily what's going on in terms of our it's based on our resistors and not necessarily what's going on in our op amp. So in this particular case, now we have our values. This is for this particular resistor combination. Now, you'll notice here, that's not what it's asking for. It's not asking me for the gain. It's saying, if I know what VB is, what's the range that's going to result in linear operation? So remember, our goal here is to find VA range. We want to say what is the max? What is the minimum value if VB is kind of a constant reference voltage maybe? So if we say VB, we plug that in as 4 volts, we can plug that into here, and we can say V naught looks like, well, that just becomes 20 minus 5 VA, and we want V naught to be, we want the absolute value of that to be less than or equal to our control voltage, right? We're basically saying, hey, if we've got this, we want that V output to be between our two values, right? That's one of our control, or one of our ideal conditions, is that our V naught is going to be between those two values. So we're saying this is 10 volts and negative 10 volts. So basically this is just a linear equation that we can evaluate. It's basically a linear inequality, sorry. We're going to plug that linear inequality in here. Plugging that in, I'm going to subtract 20 from all of these values. Subtracting 20 gives me negative, excuse me, negative 30 minus 5 volts, 5 VA is less than negative 10, and then kind of rearranging this, dividing everything by negative 5. We're going to kind of invert all of this. Remember this, when we divide by a negative number, it's going to invert all of our signs. So this kind of flips. This becomes our minimum, and this is going to move to our maximum. We know that VA has got to be between these two values. And I'm going to clean that up a little bit. I'm going to call this 2 volts right there.